Greetings. Today we will discuss Quicksort, its background, and how it works. First, let's define the sorting algorithm. Quicksort is a sorting algorithm that uses a divide and conquer strategy to sort an array. This means it breaks down a large problem into smaller subproblems, solves them independently, and combines their solutions to solve the original problem. Quicksort is particularly powerful because it can sort an array very quickly on average. So, how does the divide and conquer method work in Quicksort? The algorithm starts by selecting a pivot element from the array. It then partitions the other elements into two sub-arrays. Those less than the pivot and those greater than the pivot. This process is repeated recursively for the sub-arrays, effectively breaking the problem down into smaller and smaller pieces until they become simple enough to solve directly. Finally, the solutions to the subproblems are combined to produce the overall sorted array. More details will be discussed later. Let's take a quick look at the history of Quicksort. The algorithm was developed by Tony Hoare in the early 1960s. While studying at Moscow State University, Hoare received a job offer from the National Physical Laboratory to work on machine translation from Russian to English. He needed an efficient way to sort words stored on magnetic tape, which led him to develop Quicksort. Initially, Hoare struggled to implement the algorithm using the Mercury autocode language. However, after attending an Algo 60 class, which supported recursion, he successfully programmed Quicksort. His paper on Quicksort was published in 1961, followed by another in 1962, significantly impacting computer science. Now, what are the pros and cons of Quicksort? On the pro side, Quicksort is in place, meaning it doesn't require additional memory for the elements being sorted, just enough to track recursion and pointers. It's also highly efficient for large dataset with good average performance. However, there are some cons. Quicksort is not stable, meaning it doesn't maintain the relative order of equal elements. Additionally, it can suffer from poor worst-case performance, which occurs with bad pivot choices. In summary, Quicksort is a powerful sorting algorithm ideal for large datasets due to its efficiency and low memory usage. However, it's not always the best choice for application requiring stability or those prone to worst-case scenarios. The next member will discuss how Quicksort works.
Alright, so at this point of the lecture, we will go through the overview of how Quicksort algorithm works or how it is done. I have prepared here with me a short animated presentation for us to clearly visualize how Quicksort works. So first, let us name the parts. We have here a given unsorted array of 9 elements that contain randomly arranged numbers. Second, we have here two counters, namely I and j. So for our first step, we have to choose our pivot element. This is a crucial step in the Quicksort because the whole process of partitioning the elements will be centered around this pivot element. We have different types of pivots, which will be further discussed later on in this video. But for the sake of the overview, let us choose the last element as our pivot element. Alright, so in this unsorted array, we have our last element 3 as our pivot element. Notice below that we have a series of steps to follow whenever we iterate our counters. Instead of me going through each decision-making steps, let us try to quicksort this given unsorted array to clearly understand the process. So for our next step, we have to iterate j. J now indicates index 0 in our unsorted array, which is equal to 8, or the jth element is now equal to 8. So for our first if statement, we have to ask, is our jth element, which is 8, greater than our pivot element, which is 3, which is true. So based on our decision-making step, we just have to pass, or we just have to iterate j. So iterating j, we have now j is equal to 1. Or rather, the index j is equal to 1, because the indexing in our array starts from 0. So our jth element now is equal to 2. So again, we have to ask, is our jth element, which is 2, greater than our pivot element, which is 3, which is false. Now we have to ask again, for our second if statement, is our jth element less than or equal to our pivot element? Is 2 less than or equal to 3? Yes, because 2 is less than 3. So, based on our decision-making step, we have to iterate I. Note here that j here is equal to 1 and I here is equal to, will now be equal to 0. Because indexing in our array starts with 0. We have 0, 1, 2, 3, 4, and so on. After iterating I, we now have to ask, is j greater than I? Note here that j is equal to 0, or rather j is equal to 1, and I is equal to 0. Notice here that we are talking about j and I as counters and not the elements themselves. So, since j is greater than 0, is greater than I, we have to swap the jth and the ith element. So, we have to swap 2 and 8. So, swapping them. Alright, so notice here we have already swapped 2 and 8. So again, we have to iterate j. Our jth element now is equal to 4. And then we have to ask again, is our jth element, which is 4, greater than our pivot element, which is 3? Yes. So again, we have to iterate j. So after iterating j, we have to ask again, is our jth element, which is 7, greater than our pivot element, which is 3? Yes. Again, iterating j, we have to ask again, is our jth element, which is I, greater than our pivot element? No, because I is not greater than our pivot element 3. Or rather, 1 is not greater than our pivot element 3. So we have to go to our second if statement. Is our jth element less than or equal to our pivot element? Yes, because 1 is less than 3. So again, we have to iterate I. So after iterating I, we have to ask again, is our counter j greater than our counter I? Since j is equal to 4 and I is equal to 1, this is true because 4 is greater than 1. So we have to swap our jth element and our ith element. We have to swap. So notice here that we have already swapped 1 and 8. So after iterating j again, we have to ask, is our jth element greater than our pivot? Yes, because 5 is greater than 3. So we have to iterate j again. Now, is 6 greater than 3? Yes. Now, iterating j, we have to ask again, is 9, our jth element, greater than our pivot element, which is 3? Yes. So we have to iterate j again. So notice here now that our jth element is equal to our pivot element. So since j is not greater than our pivot, we have to go to our second if statement. Is our jth element now less than or equal to our pivot? Yes. So we have already iterated I. I now is equal to 2. And j now is equal to 8. So after iterating I, we have to ask again, is j greater than I? Since 8 is greater than 2, we have to swap the jth and the ith element. So swapping them, this will give us this array. Notice here that 3 now is in its proper order, or it's now in its proper position. Why? Because all elements on the left of 3 is smaller than our pivot element, and all elements on its right is greater than our pivot element. Notice here that 2 and 1 is smaller than 3, and the remaining is greater than 3. So after going through this step, we will now proceed to our next step, which is the partitioning. Now since 3 now is in its proper index, or now on its proper position, we will not change it. So we now have two partitions, the smaller ones and the greater ones. So we just have to repeat the whole step. So first, we have to again choose our pivot element for each partition. So for our partition 1 or subarray 1, we have our last element, which is 1, as our pivot. And for our subarray 2, we have 4, the last element, as our pivot element. So repeating the whole process again, for subarray 1, after iterating j, we have to ask again, is our jth element, which is 2, greater than 1, our pivot element? Yes, so we just have to iterate j. So after iterating j, we have to ask again, is our jth element, which is 1, greater than our pivot element? No, because our jth element and our pivot element is equal. So since they are equal, we have to iterate I. Notice here that I now is equal to 0 and j is equal to 1. So after iterating I, we have to ask again, is j greater than I? Since 1 is greater than 0, we have to swap the elements. So after swapping the elements, notice here that 1 and 2 are in its correct order. Why? Because the elements beside 1, which is 2, is on its right, because 2 is greater than 1. And the remaining elements of 2, which is 1, or beside 2 rather, is on its left, which is smaller than 2. Alright. So, repeating the whole step for subarray 2, we will have this array. Notice here that all the numbers now are on its proper position. Note that for subarray 2, you need to partition it 3 more times to arrive with the sorted subarray. So, after partitioning the elements, we just have to merge them. Merge all the partitions of this, or merge all the subarrays to come up with this sorted array. So basically, that is how That is the overview of how Quicksort algorithm works. So again, for our Quicksort algorithm, first we have to choose our pivot element. After choosing a pivot element, we have to follow this decision-making step to properly sort or to find the proper order of our pivot element, which is all elements on its left is smaller than our pivot element and all its element on its right is greater than our pivot element. After that, we have to partition the array over and over again and repeat the same process until we come up with this sorted array.
Guided by the overview of the quicksort algorithm, we delve to the importance and strategies in choosing a pivot element. So why is the pivot element important? So the pivot element serves as a reference point to partition the array into two subarrays, determining the number of comparisons and swaps of the algorithm, directly impacting its performance. So, the performance of the quicksort algorithm is dependent on the pivot element, which determines the partitioning step, recursive division of array, and depth or number of times of recursion. So now we present the pivot selection strategies in implementing the quicksort algorithm, namely the first or last, random, and median of three pivot selection strategies. We will also discuss the time complexity for each strategy. So first is the first or last element as a pivot. This selection technique selects the first or last element in the array as the pivot. It is simply to implement, and it can lead to selecting the largest or smallest element, or even the n-1 largest or smallest element, leading to imbalances in array partition. So the worst case scenario occurs when the pivot selection consistently creates very imbalanced partitions, such as the array below having only one element in the right subarray. So the worst case time complexity is O of n squared. With this pivot selection, it is also possible to have an average case time complexity of O of n log of n. So next is the random element as a pivot element. So this technique selects a random element in the array as the pivot. It is also simple to implement, and it avoids consistently picking the largest or smallest element, improving average case performance, but it may still lead to imbalances. So Quicksort typically achieves an average case time complexity of O of n log n when the partition resulted into two subarrays of roughly equal size, as shown below, with the left subarray having two elements and the right subarray having three elements. Lastly is the median of three pivot strategy. This strategy selects the median value among the first, middle, and last element in the array as the pivot. It is complex to implement, but it creates more balanced partitions compared to random selection. This leads to potentially faster sorting times on average. So Quicksort achieves its best case time complexity when the pivot effectively divides the subarray into two roughly equal partitions in each recursive call. This leads to a logarithmic depth in the recursion tree log n and a linear time complexity for comparisons and swaps within each level O of n. So as seen below in this array, the array is divided equally into two subarrays with three elements in the left side and three elements in the right subarray. So that's all for the pivot selection strategies and their time complexities.
Now that we've gone over the overview of how the quicksort algorithm works and the strategies for selecting its pivot element, let us go over an important concept in every recursive function, which is the base case. First, let us briefly define a base case. So what is a base case? It is the condition in a recursive function that tells the function when to stop. It is the most important part of every recursion because if it is not included in the condition, it will result in infinite recursions. Or in simpler terms, the program will go into an infinite loop. Next, we will define the difference between a base case and a recursive case in a recursive function. First, the base case tells the function when to stop calling itself, while the recursive case tells the function when to keep calling itself. For a simple example, the base case and the recursive case are a common occurrence for if-else statements and while or do-while loops. It is important to always include a base case in every recursive function, or else the function will never know when to stop calling itself and will result in an infinite recursion that might crash the application. Now, we will define the base case specifically for the quicksort algorithm. Quicksort works by sorting several subarrays. In quicksort, the base case refers to the condition that stops the recursive calls of the function and signifies that the subarray has already been sorted or does not need any more sorting. The base case of a quicksort algorithm is an array with less than 2 elements, because then no sorting would be required. The two common scenarios are when the array is an empty subarray or when the array is a single element array. To briefly define both cases, an empty subarray is a subarray that has 0 elements, and thus is already considered sorted and no further action is needed. In this case, the recursive call would simply return without any modifications. Meanwhile, a single element subarray is a subarray that only has one element, which is then considered to be inherently sorted by itself. Some implementations might explicitly check for this condition and stop recursion when the subarray size is equal to 1.
We need to find the first, middle, and last elements, and then sort them, then swap the middle with the second to the last element, and then make it the pivot. Now, we'll place the I counter on the first element and the J counter on the pivot. Now the role of the I counter is to find the elements greater than or equal to the pivot, and the J counter is to find the elements less than or equal to the pivot. Now we would ignore the first element and the pivot because they are now properly placed. So we'll proceed to the next elements. So if the conditions are true, we will grab the elements and then swap them. Now we will keep doing this until the I counter and the J counter cross. Here the I and J counter have already crossed, so now we would have to swap the I counter with the pivot. And then place the J counter to the left of the pivot. And now we have created a new partition. So now we will do the same process to the left partition. Find the first, middle, and last elements, and then sort them. Then swap the middle with the second to the last element. And then make it the pivot. Then place the counters again. Then keep swapping the elements until they cross. Now the I counter have crossed. So now we would have to swap the I counter with the pivot. And then place the J counter to the left of the pivot. Now we've created a new partition. So we would repeat the process in the left partition again. Find the first, middle, and last elements and sort them. Then swap the middle to the second and last element. And then make it the pivot. Then place the counters again. Then keep swapping the elements until they cross. Now the I and J counter have crossed, so now we would have to swap the I counter with the pivot. And then place the J counter to the left of the pivot. So now we've created a new partition. Again, quicksort the array by finding the first, middle, and last elements and then sort them. Then swap the middle element with the second to the last element. And then set it as the pivot. Then place the counters. Then swap the elements until they cross. Now the I and J counters have crossed, so now we would have to swap the I counter with the pivot. And then place the J counter to the left of the pivot. Now we've created a new partition. Then we'd sort the left partition. Now this is by default sorted, so we would move one step up, then move to the right partition, sort the first, middle, and last elements. And now this subarray is now sorted. We would move back up. Now this array is already sorted too, so now we would move one step up again. So proceed to the right partition. Now this already sorted. Move back up again. Now this array is already sorted. We would move one step up again. And proceed to the right partition. Do the same. Now this subarray is now sorted. So now this entire subarray is now sorted. So again, we move one step up. And now we would sort this right partition by finding the first, middle, and last elements. Then sort them and swap the middle to the second to the last element, and then make it the pivot. Place the counters, swap the elements until they cross. Now the I and J counter have crossed, so now we would have to swap the I counter with the pivot, and then place the J counter to the left of the pivot. And now we've created a new partition with the 33 on the left, which are already sorted. So we would move one step up so that we can proceed to the right partition, which would need to be sorted. So now we would find the first, middle, and last elements again, sort them, and then swap the middle with the second to the last element, and then make it the pivot. Place the counters, swap the elements until the counter is crossed. Now the counters have crossed, so now we would have to swap the I counter with the pivot, and then place the J counter to the left of the pivot. Now we have created a new partition again, so we'll repeat the process in the left partition. Find the first, middle, then sort them, which is already sorted. Now swap the middle to the second to the last element, which is it's already second to the last element, so no need for that. Now we would set it as the pivot, then place the counters, now the counters have crossed, so now we would have to swap the I counter with the pivot, and then place the J counter to the left of the pivot. So now we've created a new partition. Proceed to the left partition, which is already sorted. So we would move one step up. So proceed to the right partition, which is already sorted. So now we would move one step up again. Now this subarray is now sorted, so we would move one step up, and then proceed to the right partition, which is already sorted. So now we would move one step up again. Now this entire subarray is now sorted, so that is ready for us to move move up. Now this subarray is already sorted, moving up again, and now this entire array is now sorted.
Now, we're going to tackle the code implementation of Quicksort algorithm. So, this has already been tackled earlier by Aivann Martinez, but we're going to explain further about the process and pseudocode in implementing the last element as our pivot. So, with these numbers, as given in the ComSci 123 PDF, starting off with these counters, I considered naming I or J as low or high, respectively, but for other books, it can be called as start or end. So looking at these counters, we can see that I is placed before index 0. Here, outside, take note, I is placed before index 0, and J is placed at index 0. J, this is J and this is I. So, looking at the condition, the first condition is to make the final index as our pivot, which is 3, here. Since we do know how the following process written below works here, we consider index 0 starting from 33 until index 8 as pass due to the condition here, if J is greater than pivot, then pass. Next, now we consider this next condition. For J at pivot, we follow I plus 1, then swap J and ith element, specifically swapping index 0 and index 9, or 33 and 3 respectively. So next, we do know that 3 is sorted and swapped to index 0. But then we need to create two subarrays by partitioning our previous pivot 3, which makes partition at index 0 containing separate recursion of smaller and greater. But since there is no smaller subarray in the partition made, we only consider the greater subarray here, which is from 50 to 33. Next, we do a quicksort in the greater subarray as we have done in the previous array in the given processes below. Since 50 to 48 are greater than 33, we call it pass again. So, moving on, since for 29, since we do know that 29 is smaller than 33, we follow the second statement here. Else if J greater than or equal to pivot, then we add 1 to I. So we move I to index 0 corresponding to 50 as it was from the outside. So basically explaining that this I from the outside, it goes at index 0 since it has the condition here I plus 1. So another condition is J is greater than I for counter, mentioned by Aivann Martinez earlier. Since J is greater than I in counter, we swap the J and ith element, 50 and 29. So now we can see that 50 and 29 are swapped. But moving forward to the next index here, 30, we can see that it is lower than 33. So again, we follow what is said in the else if statement. But of course, how does the swapping work if we do implement this in our code? So let's have a variable here, temp. This works by assigning a temp variable and equating this to the current array I. Here I. We equate temp to I. So it's going to move there, making the value 42 to temp. So now we equate array I to array J. So what will happen? It will move there, making 30 move to I. So lastly, we equate array J to temp. So what's going to happen is 42 will move there. So the swapping is now complete, having 30 in I and 42 in J. So for the pseudocode, in this implementation of swapping, the function is shown, be it like this. Same as what explained earlier, we just equated each variable until the swapping process is complete. So I already explained it, it's just here. Temp is equals to array I is equals to array J is equals to temp. So next, we continue on moving to the next array. So we can see here, from 42 we move to 43. But since 43 is greater than 33, we pass. And same process, you can see 16 is lower, so we swap. Again, same process, 5, we do swapping again. So for finally, In the last condition, in this subarray, jth at pivot I plus 1, then we swap jth and ith element. Specifically, swap 33 and 42. And now we can see that everything left of 33 is smaller and everything right of 33 is greater, which makes 33 sorted, which can be seen in this divided parts. As shown in 3 and 33, we can see that they are already sorted, so they have constant positions. So 3 is at index 0 and 33 is at index 5. Since we still have another smaller subarray and greater subarray still not sorted, the process continues in the respective subarray with pivot at last element. So we can see here 5 pivot and 42 pivot. So they are different basing on the subarray. So continuing of merging of all sorted subarrays, you can come up with this sorted array with values 3, 5, 16, 29, 30, 33, 42, 43, 48, and 50. So this is the final sorted array for if you continue on doing this implementation. So for the pseudocode of partitioning, it was already shown, but of course, explaining further here, we initialize two variables first, pivot and I. The pivot in the second line establishes that the pivot must be the last element, which in the first illustration is 33. For I in the third line, here, I is equals to low minus I, we do know that it is outside at first. So we can see an arrow here in the first illustration that it came from the outside before it reaches index 2. Index 1 rather. And now for loop part, we assign a parameter j from low to high. So looking at the second illustration, the if statement inside the loop corresponds to the else if statement, wherein if j is greater than or equal to pivot, then I plus 1, then swap the two elements if j is greater than I. Basically, just following the conditions, but more of in an efficient way of code. And finally, outside of the loop here, swap and return I plus 1, we return the value of the pivot in the given line code, return I plus 1, which will then be used for partitioning in the quicksort function for recursion to be discussed later. So looking at the illustration 3 here, since 33, imagine here, since 33 was a pivot and it was swapped to 42, the one being returned here, since return I plus 1, we do know that I plus 1 is here. The one being returned here is 33. So basically, you're just returning the pivot value in the partition. So next. So lastly, for the pseudocode of quicksort function, logically, we create an if statement where as long as low is smaller than high, we do this functions until the array is sorted. So for the return I plus 1 in the last slide, in the previous slide, in the partition function, we consider the pivot as pi in order for us to separate recursion to left and right, specifically smaller and greater. So as given in the two functions with quicksort here, as you can see, quicksort. Looking at the illustration, the subarray 1 corresponds to the first quicksort function, which sorts 29 to 5. As you can see here, the first quicksort function, array low pi minus 1. And the second, or the subarray 2, which is greater, corresponds to the second quicksort function, which sorts 43 to 42. So I'm pertaining to this quicksort array pi plus 1 high. So now, since we do know this pseudocodes, let's now move on to using Visual Studio Code and implementing it in Java by applying the given pseudocodes. Okay, so now for the Java implementation of Quicksort. I based most of my code from Geeks for Geeks, and added a bit of ideas from YouTube, from Brocode and Telescope. So for public class last element, basically this is just a translated pseudocode. So it's just translated to Java. So as you can see here, the pseudocode that was mentioned in the PowerPoint for swap, as you can see here, just translated. For the partition, just translated. And lastly, for quicksort, just translated. And I just added a print function just for me to see, or for me to debug the pivot and the partition. And lastly, to print the sorted array, added new function, print r. And for the main, I already added here the 10 elements from ComSci 123 PDF and a bit of function call just for it to work. Okay, so let's run the code. Oh, so you can see here, the sorted array is 3, 5, 16, 29, 30, 33, 42, 43, 48, 50, which is just right. So looking at the initial array to until the third array, as you can notice, this was the actual answer that was made in the PowerPoint mentioned earlier. So as you can see here, that's basically the same in the initial array. So the answer made in the PowerPoint, the pivot is 3 and the partition index is 0, which is the same. And for the second, this was the array that was made by this pivot 3 and partition at index. And for the pivot 33, partition at index 5, this was actually the last answer that we made in the PowerPoint, and the final array that was mentioned was 3, 29, 30, 16, 5, 33, 43, 48, 50, 42. And if you actually continue in doing it, you'll arrive at the sorted array 3, 5, 16. So now for time complexity, we start off with the best case with an example of array with size 11. So looking at each level, we make n calculations until to the last level, which makes it big O of n. So in finding time complexity, we get the k here as height, and it's n calculation. So observe that in each level, the area size is always divided into 2 until it reaches 1. So we can write the equation as this: n over 2 raised to k is equal to 1, for which the value that we'll get is k is equals to log base 2n. So with the height being log base 2n, and we do n calculations, therefore the best case is big O of n log n. So to the average case, assume it's not divided into 50% as from the best case, but it is divided into 10%. So each pivot divides the array to 1:9 ratio and goes until 1. So calculating the levels, same process. We acquire k is equals to log base 10 over 9n. And to each level, we do n calculations, or big O of n, same as the best case. Therefore, the runtime is the same, big O of n log n. So now for the worst case, when the provided array is already sorted, let's assume that it is ascended in an ascending order. So we do n operations, but only the pivot is sorted until the end. So the equation goes like this: 1 plus 2 plus 3 plus and so on plus n. So which makes it n squared plus n over 2. Therefore, the worst case time complexity is big O of n squared. So now, analyzing the space complexity, since we do know that quicksort is a recursive function and the size of the stack is dependent to the level and height of the tree, for best case, since this is a balanced partition, the space complexity of it will be big O of log n. And for worst case, due to skewed recursion here, the space complexity is big O of N. And these are our references. Thank you.